All right, good afternoon. Before we start, just a quick announcement in case you have missed that. The last question of homework 4, the implementation question of the primal dual interior point method, we moved the due date for that to Monday, okay, to give you a little extra slack there. So that's that. So let me proceed with the story that I have for you today. I'm actually very excited about this because this is a particular topic that in previous versions of the course we have not discussed in much detail, and this gave me the opportunity to revisit this topic and remind myself of how incredibly clever and cute this particular topic is. So this is within the class of still sort of second-order methods. As we will see throughout our discussion, you realize that this is not quite a second-order class of algorithms. It's kind of, I would call it like a first and a half order algorithm. It's between first and second order. So it's some kind of convex combination of those two. So that's Quasi-Newton methods, and that is the point of the class today. Before we do that, just a quick recap. This is something we did last time, and it is related to that same question in the homework. Primal dual interior point methods, right? So here is our usual problem of interest, minimize. So some convex problem here, right? Some convex objective, affine constraints and inequality constraints that are also nice and convex, everything differentiable. If we have a strong duality and all the nice things that we could ask for, then these are the central path equations. Think about them as a tweak of the optimality conditions. As tau goes to 0 in the limit, that gives us a solution to the original problem. And then the crux of a primal dual algorithm, a primal dual interior point algorithm, is really to apply Newton's method to this block of equations. Okay, so how do we do that? Let's call that block of equations R, the residuals. And in some way, the goal, the crux of the algorithm is to aim for a solution to that system of equations. So how do we do that? We compute a linearized version of this, right? A solution to a linearized version of this. That's the Newton step. And then we take a step. We compute a step length, theta, and we move towards in the direction of that Newton step. Okay. So if you were to summarize it quickly in 2 slides, that would be it. Okay, it's essentially like based on Newton's method to the system of equations defined by the central path conditions. One detail that I answered last time, and I was revisiting my notes. I should have given a better answer to this last time, but let me try now again. So observe the following. If we are trying to solve, let's say, suppose that delta W is negative R prime W times R of W. Okay, so think about R as our R there, okay, and W as the triple X, U, and V. So suppose that delta W is that. So what happens to R of, say, W plus some small step, let's call it theta, delta W. So this is approximately, if we use a first order Taylor approximation, this is approximately RW plus R prime W times theta delta W. Okay? So this is approximately, if you play around with this, you get RW, and then you get theta RW, so let me just write it down, theta R prime W times delta W. But this guy, by construction, is negative R, right? So this is negative R of W. So this whole thing is, by construction, approximately 1 minus theta RW. Okay, so the question, someone sitting around, I think it was you were asking, how could we be sure that the line search will do the job? Well, because at least for a small step, it would clearly be the case that the size of R is, roughly speaking, 1 minus theta, 1 minus the step length times the size of the previous R. Okay, so it was much more straightforward than what I what I intended to explain kind of on the spot. Now, as long as I'm saying this, let me point out one additional little observation here. If R is linear, right? If R is linear and theta is 1, right? If R is linear and theta is 1, then of course the problem is trivialized because it's a linear system of equations. With one full Newton step, we solve it. But the same thing holds if some blocks of R are linear. In particular, if you look at the last block of R there, that is linear. If you are lucky enough to take one Newton step, then that will take care of that last block, because essentially the approximation here would be exact for that block. So in the case, for example, of linear programming, the residuals are just mildly nonlinear. That's why in linear programming, interior point methods work so well, because eventually we can take a full Newton step and then make very quick progress. So that was a quick recap of something we did last time. I have a lot of stuff that I would like to tell you today, so let me close that chapter on interior point methods and move on to what is the goal of the class today, and that is Quasi-Newton methods. So I have prepared all of this, but to be honest, I think the chances that we make it to the last point here, that's not very likely, but I'll try my best. So we'll make it through the first 4 items, maybe part of the 5th one. So I want to spend a few minutes kind of telling you what Quasi-Newton methods aim to do, what is the motivation, why do we use them. Then the main types of updates that are connected to Quasi-Newton methods. So by the time we take a break in about half an hour, you will be familiar with all of these buzzwords, SR1, DFP, BFGS, and broaden. You'll know what those mean. Then I'll say something about superlinear convergence, which is a very neat property of Quasi-Newton methods. And then limited memory, BFGS, which is tweaked on a certain type of Quasi-Newton method that actually is very, very widely used. So what's the motivation? So let's go back to a much simpler problem, an unconstrained smooth optimization problem. So minimize f of x. And I am purposely omitting the word convex in this case, because in fact, Quasi-Newton methods were initially conceived and are actually used extensively for beyond convex, for non-convex problems. So of course, everything that we're going to say here today applies to convex, but Quasi-Newton actually applies a little more more widely than just convex problems. So let's look at an unconstrained smooth minimization problem. We assume that f is nice differentiable. So let's recall our old friends, the gradient descent method and the Newton method. So gradient descent, we move in the direction opposite to the gradient. Newton method, we move in the Newton direction, right? So those are the two kind of very classic methods to solve the unconstrained optimization problem. So we discussed this in previous classes, gradient descent versus Newton's method. Newton's method has this wonderful property of quadratic convergence, right? So if you're close enough, it basically zooms to the solution. You have that quadratic convergence. To put it in terms of, say, tolerance, if you are close enough, it will suffice to take log epsilon steps. Log epsilon for any reasonable value of epsilon is practically constant. So as opposed to gradient descent that would, for a nice function be linear, right? For a strongly convex function would be linear, would be log epsilon. So that's a wonderful property of Newton's method, but then there is, of course, some trade-offs, right? Newton's method involves, if you look at it, right? It involves in principle, two important steps: compute the Hessian of the objective function, and compute the step, right? The product here, Hessian inverse gradient. So of course, computing this Hessian inverse gradient means solving that system of equations. So solving for P there. P would be the Newton step. So both of those, each one of those two steps could be computationally very expensive. Depending on the particular problem at hand, computing the Hessian could be an enormously costly operation. Solving a system of equations also could be an enormously expensive operation. So that is the motivation for Quasi-Newton methods. The motivation for Quasi-Newton methods is, well, if you think about going from gradient descent to Newton, right? From gradient descent to Newton, kind of the magic here happens because we use the Hessian. We scale the gradient by some matrix, the Hessian. So the idea of Quasi-Newton method is, how about if we do something similar here? We take an iterate that is of similar format as these two iterates. So it's sort of like a gradient, but we will put a scale here, a scale matrix here, a scaling matrix. But we are going to shy away from the full Hessian because that is expensive. What if we just use some matrix B? So this would be like taking taking P equal to B inverse gradient, okay? Where B is some approximation of the Hessian, is some approximation. And we would like B to be both easy to compute and to make this, the computation of this step also be easy. Okay? We would like both of those to be easy so that the amount of work in some way is comparable to that of the gradient. So we relieve the, if you want, the main limitations of Newton's method. So that is the idea of Quasi-Newton methods. And that's what I'm going to tell you about for the next hour. Okay? So how do we make this idea more precise, and how exactly we construct B? So let me tell you a little bit of history, because the history associated to Quasi-Newton methods, in my opinion, is really fascinating. So there was this guy, William Davidon. He was a physicist at Argonne National Lab. So this is a lab south of Chicago, where there's a lot of interesting stuff in optimization that has happened at that lab. And so he was a physicist, mid-50s. He was working on a problem related to physics. I do not recall exactly the details of the problem, but the relevant part is that he needed to solve an optimization problem. And the algorithm that he was using was a coordinate descent algorithm. We'll talk about those a little bit later in the class. And somehow the algorithm just overwhelmed the type of computer that he was using, and the computer kept crashing before he could get any kind of meaningful solution to his problem. So this guy was very frustrated with what was happening. He just couldn't get past that particular, say, calculation. So then he decided, is there a way that maybe I can tweak my calculations to speed them up so that I get a solution before the computer crashes? So that was the first Quasi-Newton method ever. Okay? The particular trick that he did we'll explain a little bit later. Now, it turns out that the contribution, the idea that he came up with, later on was picked up by two of the main pioneers of optimization, Fletcher and Powell. And it turns out that this really, really was a very, very influential breakthrough. And as it has happened from time to time in history, actually the paper that he wrote, he submitted it to a journal, and it was rejected. And then he just finished technical report, filed it somewhere, but his colleagues kept using his algorithm because they were very excited that it worked extremely well. And a whole area of research essentially was triggered by his work. So back in the 70s, 60s, 70s, 80s, Quasi-Newton methods, that was one of the most active areas of research in optimization, and actually it really helped develop the entire field of nonlinear optimization. So something interesting that happened is that in 1991, SIAM created a new journal. It was called the SIAM Journal on Optimization, which now is one of the prime outlets in optimization. And in the very first issue of the journal, the leading article was Davidon's article, the article that had to wait for more than 30 years, even though it was enormously influential. So when you guys submit a paper and get it rejected, don't be discouraged. You may be ahead of your time, okay? Now, I would like to say that in addition to his remarkable work on optimization, Actually, this guy, William Davidson, he was a peace activist. There is a really cool story about he essentially organizing a break into the FBI offices in Philadelphia and stealing some files, and it's a very interesting story. I don't want to get into that because then we don't have time to talk about Quasi-Newton methods. But if you're curious, read or take a look at this book, The Burglary. It's a book that was published right after he died in 2013. I think they were waiting for him to die before they published that so that they wouldn't out him to the FBI and everyone. So it's a fascinating story. All right, so much for the story. Let me go back to the point of Quasi-Newton methods, right? So let me put here, again, the idea, right? So the idea, again, is that we will take something that looks like a gradient step, but where we are going to include some scaling matrix here. So you can think about this. This is going to be basically, this is going to be x minus t b inverse gradient, right? I mean, if you put these two together. So yeah, so that's, we would like that b to be an approximation of the Hessian. So if you think about our iterates, let's say that our iterates are xk, so we would like bk, the b's will be updated as part of our iteration. The bk should be an approximation of the Hessian at xk. In particular, if you think about it, think about what the Hessian does, right? The Hessian is the derivative of the gradient. So if you think about the Hessian should act as if it were the derivative of the gradient. So if you think about the first order Taylor approximation for the gradient, right, near xk, the approximation that we are trying to come up with should do that job. Okay, so the approximation should satisfy that first equation there, at least approximately, the b. Now, once we take a step, right, once we go from xk to xk plus 1, then we would like to update our approximation to the Hessian. We would like to update our b. So once we go from xk to xk plus 1, we would like a new bk plus 1. And the key idea is that we don't have to start from scratch. We can use the information that we already had in bk. So bk is like a warm start for our new approximation to the Hessian at the new point. So use bk as a warm start for our new approximation to the Hessian. So think about bk as we are trying to guess what the Hessian is in some way. And we are sharpening the guess that we had previously at iteration k. So here is a reasonable requirement for bk plus 1. Okay, a reasonable requirement for bk plus 1 is that at bk plus 1, how about if we have it, since we have freedom on how we update bk plus 1, how about if we have it set so that the equation up there holds exactly for the new update, for the new bk, I guess bk plus 1. New b, we are going to enforce the equation that is at the top here, okay? So if we just move things around, right, move the gradients to one side, you get that bk plus 1 sk is equal to the difference of the gradients, okay? So that would be something, you know, again, if we are going to adjust our approximation to the Hessian, this seems like a very reasonable requirement because it would be a way of, say, stating that that approximation is at least satisfies this equation. So that is called, let me put it here. That equation goes by the name of the secant equation. So this equation is the secant equation, and it's typically phrased the following way. We simply put bk plus 1 times sk equal to yk, where sk, right, sk is understood to be the update, right, the change in the main iteration from xk. You go to sk plus 1 by adding sk. So sk is the difference in x. Okay? Sk is the difference in x. And yk is the difference in the gradients. All right? So it's called the secant equation because if you had, say, linear terms, right? If you had linear, you would have a picture that would look something like this. So if you had, say, if this was xk and this was xk plus 1 equal to xk plus sk, right? And you had here gradient f xk and gradient f xk plus 1, right? So the secant equation, the secant equation would just tell you that this slope here should be bk plus 1. Okay, so it's like if you took two points on the graph of the gradient and wrote the secant line that goes between those two points. Okay, so that's called the secant equation. Secant equation. So again, it's motivated by this, right? And it's typically abbreviated with this notation. So this is the notation that we'll rely on. So S will indicate the difference in the iterates, and Y indicates the difference in the gradients. Okay? And of course, it's easier, just to avoid writing so many indices, to write B plus S equal to Y. Okay? So the S will be understood as the difference between two consecutive iterates, and the Y, the corresponding to difference between the gradients of those iterates. So now, if you think about, of course, the one-dimensional picture that I just flashed here is misleading because once you enforce the secant equation, it's clear what the slope should be, right? But if these are vectors, right, if S and Y are vectors, there are many ways that I can ensure that I can satisfy the secant equation. Okay, the secant equation only gives me n equations, but the matrix has n square entries. So, you know, there are many solutions to that. So we would like, among all those solutions, we would like the new B plus to be symmetric because it's meant to be an approximation of a Hessian. We would like it to be close to B because, again, B presumably already contains some information about the Hessian. So we would like B plus to be close to B. And this is important since B is, again, meant to be, since the B's are meant to approximate Hessians, we would like to preserve positive definiteness. Okay? And this, of course, will be especially relevant for convex problems. We would like to preserve positive definiteness, meaning if the previous B is positive definite, we would like the update to be positive definite. So these are the conditions that we would like to enforce, all right, for the update on B. Yes, question?
If you compare the top equation and the middle equation on that slide, on your right, isn't that just pushing bk plus 1 to be equal to bk? Because the left-hand side is the same, because xk plus 1 is xk plus sk.
So I'm sorry, are you talking about here?
Yeah.
So let's see. So
compare the terms on either side.
no, because BK I chose before I chose SK, right? BK I chose at iteration K. I didn't know what XK plus 1 was going to be. XK plus 1 I compute based on BK. So the first equation may hold only approximately. This guy we are requiring to hold exactly. And that is in some way a key ingredient of how Quasi-Newton methods are going to work. Okay, so that's a good question, but yeah, this does not hold for BK, okay? Because this guy is not yet defined when we construct BK. All right, so those are the three properties that we would like to enforce. So let me keep them here for a moment. We would like, this is the secant equation, and in addition to the secant equation, we would like those three properties, okay? So the first, let me describe what is probably the most straightforward type of update, the symmetric rank 1 update. So this update is simple. It satisfies the secant equation. All the updates that we'll discuss today satisfy the secant equation. It maintains a symmetric matrix. And the update is close to the previous one in the sense that it's just a rank 1 update. Unfortunately, it doesn't necessarily ensure the last property here. So it has some limitations, but in spite of that, it's something that people use. So the idea is quite simple. You want the new approximation B plus, the new Hessian approximation, to be a rank 1 update. So that's what gives it the name, rank 1. So we want to add a very simple matrix, a rank 1 matrix. In some way, this has been very, what is the word that statisticians like to use, right? Parsimonious, right? We are adding the most parsimonious type of change to the matrix, just at rank 1, a rank 1 change. So a multiple of U transpose. Now, if you plug that type of matrix in the secant equation, right? So let me write this down. This is very simple. So if B plus is B plus A U transpose, right? Then B plus S is BS plus A U transpose S, right? Now this is a scalar. This is a scalar, so this is BS plus the scalar is all of this times U. Okay, and that that is supposed to be, this is the secant equation, right? Secant equation. That is supposed to be Y. So if we move things around, we get that A U transpose S, which is a scalar times U, is Y minus BS. Okay, Y minus BS. Now, here's a very simple observation. It's simple, but it's key. Here, you get, this is just a scalar times a vector, right? And on the right-hand side, you have a vector. The only way that those two things could possibly be the same is if the vector U is a multiple of the vector on the right-hand side. Because other than that, all we are doing on the left-hand side is multiply by a scalar. Okay? So you can then, if you want a rank 1 update, and if you want the secant equation to hold, then you're necessarily restricted to taking U to be a multiple of that difference, Y minus BS. So if you take U to be a multiple and then look at what multiple it should be, you can just plug that back here and solve for the equation, solve for A. You get that this is what you need to get. So the A essentially turns out to be 1 over the product Y minus BS transpose S. So that's your Y. And this is called the symmetric rank 1, okay? SR1, the symmetric rank 1 update. Now, there is something that is nice about this rank 1 update. And let me, as I often do, let me keep it here. So this is the symmetric rank 1 update. The rank 1 matrix that we are adding is like this. So there is if you think back to how we are going to use our B's, right? How we are going to use our B's. Our B's will be used this way. We want to use the B's as part of some algorithm, right? So we want to use the B's in equations of this form. We are interested in the inverse of B. So we are interested in the solution to an equation of this form that involves B. So it turns out that having B would be nice. It would also be nice if we can update the inverse of B, okay? The inverse of B. So yeah.
Do we need B plus to get Y? Like, because from the update rule, like X, like the update rule in the previous slide, it defines like the next term of the gradient of F in terms of BK plus 1 times SK. So don't we need like B plus to get Y in the first place?
I'm sorry, what do you mean when you say to get Y?
So we use BK plus 1 for the next update step to get XK plus 1.
Yes.
Right? So
No. We use BK to get XK plus 1. Okay? Yes. So maybe I should put that here. Yes, just to be clear, maybe I should write that down. Just to be clear, a Quasi-Newton method would work like this. Just to be clear, the main iteration in a Quasi-Newton method okay, we first compute, pk, this is going to be minus b, oh, well, I guess I mess up the indices and sub-indices, so let's be patient with me. So we compute this guy, right? This is our direction. And then we set xk plus 1 to be xk plus some step length, let's say tk times pk. Okay? Then the third step would be now update bk plus 1. Okay. So we go in that order, right? So yeah, I guess maybe there was some value to keeping all the indices there. So okay.
If you go back to slide 10.
Yes.
So in the bottom equation, where we calculate b plus, we're effectively using s, but s is xk plus 1 minus xk.
No, the s here, so maybe let me write this down with all the relevant indices. So the S1, SR1 update, if you put all the indices, is bk plus 1 is bk, and then we have yk minus bk sk, yk minus bk sk transpose divided by yk minus bk sk transpose sk. Okay, so that is the update, the update with all the relevant indices. Okay, I realize now as the discussion goes that maybe I was a little too, maybe the lack of indices left the notation too bare. Okay, but if you were to put all the indices, it would be like this.
Well, sk is defined by xk plus 1 minus
sk is the difference between xk plus 1 minus xk. And yk is the difference gradient f xk plus 1 minus gradient f xk. Yes. Is that the question?
Yes, sir.
So I think it's just a matter of keeping your indices right in your head. Like at iteration k, we have xk, bk. We use those to compute xk plus 1. But then we need to worry about how we are going to update b to bk plus 1. So that's where all of that junk comes into play. So here. Okay? So again, this is the rank 1 update. And as I was saying a minute ago, actually right here, you see that actually we will need to solve a system of equations with b. Yes?
So I couldn't follow how we can get u in the final step.
Oh, okay. The key here is that you have u has to be a multiple of y minus bs. So let's say that u is equal to y minus bs times, if you want, lambda, or b in the front. If you plug that guess for you here and solve, you get this expression, okay? As I often respond to students when they ask me a question like that, maybe that should be a good homework exercise. So anyway, it's a simple calculation. It's really not, it's a couple of steps that I omitted here, that I skipped. So let me keep again, back here, right? We want to solve something with b. So it's convenient if we could update, and this is the kind of insight that I'm sure when people back in the 70s were working with this insight seems so many years later obvious, but back then probably took a good number of, say, months, if not years of research and discussions to figure that, wait a second, This is fine, and this is a nice update on the approximation to the Hessian. But it would actually be more useful if we don't get an update on the Hessian, but an update on the inverse of the Hessian, because that's the one that we need to compute the relevant step at each iteration. So it turns out that if we have this kind of update on a matrix, and if we already have the Hessian, the inverse for the matrix, then updating the inverse of this update is also easy. So here it is. This is a famous formula that was due to these three guys. It's called the Sherman-Morrison-Woodberry formula. Essentially, the formula is that if you already have the inverse of a matrix, let's say if you already have the inverse of A, and you update A with a low rank matrix, then the inverse of A also gets updated with a low rank matrix. And the formula tells you exactly how. So if we have A and we add U V transpose, where U and V, so U would have the same number of rows as A. Okay? Both U and V have the same number of rows as A, but potentially fewer columns. So here, D is typically much smaller than N. Then the inverse of this sum is the inverse of A minus this expression here. Okay? Oh, dear, I think I am missing actually a term here. Yes, I'm sorry, I am missing a term here. There is a V transpose that I'm missing here. Sorry about that. Yes, this doesn't make sense, right? Because this is a small matrix. This is D by D, and this is N by N. So I'm missing a V transpose here. So I only noticed that now, so sorry about that. This should be the Sherman-Morrison-Woodberry. There should be a V transpose here. Okay, right here. Yeah, that's a big typo. So let me give you a special case that actually comes in handy for the Quasi-Newton updates. Of Sherman-Morrison-Woodberry. So if you have A plus UV transpose, so if it's just a rank 1 update, okay, so if these are vectors, this is the inverse of that is A inverse, and then you have A inverse U, V transpose A inverse, 1 plus, so 1 plus V transpose A inverse U. Okay, so this is the Sherman-Morrison-Woodberry. So if you think about the SR1, the SR1 is a rank 1 update on B. It turns out that then gives a simple rank 1 update on the inverse of B, like this. So this H plus is the inverse of this matrix. Okay, so the S1 update has this advantage that both the update and the update to the inverse, they're simple rank 1. So this is maybe the simplest type of Quasi-Newton update. It's simple, but it has two shortcomings. If you think about either that expression there or this expression, the expression for B, this expression here. So either for the approximation to the Hessian or for the approximation to the inverse of the Hessian, there is a term here in the denominator that could potentially create a headache. It could be the case that that term is small, maybe even 0, when the numerator is not 0. So the SR1 update could potentially fail if we have that this product is too small. And another problem is that the SR1 update does not necessarily preserve positive definiteness. So that's kind of a shortcoming. So let me tell you about what are the most commonly used updates. So there are two main ones, and they are very similar. These are called the DFP update and the BFGS update. So the DFP update is, the DFP is after the discoverers of the update. Davidon, the guy that I mentioned earlier that had that brilliant idea while he was at Argonne National Lab. And then Fletcher and Powell were, so Davidon was not an optimizer. He was actually a physicist. And he actually did very little work on optimization. But what he did was extremely, extremely influential. And then Fletcher and Powell, they were like mainstream optimizers. They both were professors at Cambridge. Apparently, they were not good friends, even though they had offices apparently across the hall from each other. This was one of the few times that they collaborated when they did this. They both are very well known, and they did a lot, but rarely together. You know, it happens. Unlike Carnegie Mellon, where we have a nice culture of collaboration, right? So the DFP update is based on a small tweak on the previous update. The small tweak is that why don't we go a little beyond rank 1? Why don't we use a rank 2 update? So a rank 2 would be, instead of adding just a UU transpose to either the B matrix or the H matrix, why don't we add 2 matrices of that form? So that's a rank 2 update. So again, you can apply the same trick. If you look at the secant equation, then the secant equation, if you write the secant equation in terms of H instead of B, so let me write down something here, a little observation here. The secant equation, just to reiterate, so the secant equation is Bs equal to y. And of course, this is completely equivalent to if we can think in terms of B, the approximation to the Hessian, or H, the approximation to the inverse of the Hessian. This is completely equivalent to Hy equal to S. So the secant equation, if you multiply H by Y, then, and you reorganize the terms again, you should have, you know, to be more precise here, the secant is supposed to hold for the next term, so it's like that. The secant equation then gives you that S minus Hy should be, the rank 2 update should satisfy that equation. So what you could do then is try to fiddle with U and V, make the choice of U and V that allows you to satisfy that equation. So this is not uniquely determined as in the SR1 update. But instead, you can make a guess. Let's say take U equal to S and V equal to Hy. If you plug in those values in the previous equation and then proceed and solve for A and B, it turns out that you get this update. So the update on the inverse is like this. So it's a rank 2 update where now the U and the V are like Hy and S. So that's the update on the inverse. And if you apply again the Sherman-Morrison-Woodberry inverse formula, the update on B, which is the inverse of this guy, turns out to have this expression. Okay, so that's nice. That is the Davidon, Fletcher, Powell update. Okay. Now, there is a nice advantage of this update over the previous one, which is the following. Suppose that B is positive definite. Okay, suppose that B is positive definite. Then this whole thing here, it's easy to see that that whole thing there is, again, at the very least, positive semi-definite. So it turns out that if this guy is positive definite, and this is positive, then the whole thing is positive definite again. So that was one drawback of the SR1 update, the rank 1 update, that is corrected with the rank 2 update. So that is satisfied here. There is also an alternative way of deriving the DFP update. It's kind of a neat alternate derivation that instead of looking for a rank 2 update directly, you look for a matrix that is close enough to the previous matrix, okay? A matrix that minimizes some kind of norm to the previous matrix that is symmetric, satisfies the secant equation. And it turns out, I'll have you work on this in the next homework. It turns out that if you choose that norm appropriately, you get, again, the DFP update. So how do we choose that norm? We have to do a couple of things here. This gets a little bit more technical. So first, if we want to preserve positive definiteness, and if we want to enforce the secant equation, so the secant equation is written one more time there at the top, b plus s equal to y. If we want that, and we want positive definite, right? We want b plus to be positive definite. If we pre-multiply by, say, by s, right? If we pre-multiply by s, then we get the product s transpose b plus s. That has to be positive. But that product, if the secant equation also holds, is the same as y transpose s. So if we want to have any hope of preserving positive definiteness, then y transpose s has to be positive. In all the literature on Quasi-Newton methods, this is called the curvature condition, that y transpose s be positive. That is the curvature condition. And then there is this neat fact. If we have two vectors that satisfy the curvature condition, if the two vectors are, they make an acute angle, right? If their inner product is positive, then you could always find a symmetric and positive definite matrix that sends one to the other. So there is always a symmetric positive definite M such that MS is equal to W. So then the DFP update, another way of obtaining the DFP update is to solve this kind of weighted minimum Frobenius norm problem where we are looking for the matrix B that is closest, the matrix B plus that is closest to B, that satisfies, that is symmetric, that satisfies the secant equation, and that minimizes this norm here where we have this weight here, W. The W is just any non-singular matrix that makes this equation hold. Okay, so the W could be any kind of, for example, the Cholesky factorization of M, where M is a matrix that sends S to Y. So what is somewhat remarkable, and this is the kind of stuff that you can appreciate only if you work through the calculations, so that's why we'll have you do that. When you solve that minimization problem, so this is a problem with the a problem that where we are minimizing over the space of matrices. So when we minimize that, what we get is, so let's see, I had, here's my rest, yeah, here, okay. When we minimize that, so when we solve that problem, it turns out, and this is like magic, we get exactly the DFP update. When you solve this, the solution to this problem is exactly the DFP, that is that H here, this H. This is the solution to, oh, sorry, not, I guess if I set the problem in terms of B, I should say not H, but B. This B turns out to be the solution to this problem. So that is the DFP update, okay, DFP. So you can think about it being derived two ways, as proposing at rank 2 and then plugging into the secant equation and solving, or as solving a norm minimization problem with an appropriate weight here and Frobenius norm. So as it is customary, why don't we take a very, very quick break in case you need to take a breather, right? I do. So, and then I'll tell you about the BFGS update, which, just to give you a reason to come back and to be attentive, the BFGS is the most popular update out there. So let's take 5 minutes. This is the DFP update for the inverse or for H and for B, right? Either the approximation to the Hessian or the approximation to the inverse of the Hessian. And then I want to just reiterate two possible derivations for DFP as a rank 2. You propose a rank 2 and then you play with it, or as the closest matrix to the previous one according to this weighted Frobenius norm. Okay? So those are two possible ways of thinking about DFP. Now let me mention this other update that is closely related. This is by Broaden, Fletcher, Goldfarb, and Shano. So Fletcher is the same Fletcher from the DFP update. So he was very, very active on this for a number of years. And then Goldfarb, he's a character. He's still around and very active, very, very active even today. He's a professor at Columbia. Shano was a professor at Princeton for many years. I never got a chance to meet Broaden. So anyway, all of these guys, of course, were very actively working on Quasi-Newton method. And the update that I'm about to describe, the four of them developed that independently, which is not surprising, right? Many people are working on what is a hot problem. It turns out that this update, which is, again, today, so many years later, it seems like such a simple tweak on the DFP update. It took a good number of years and 4 different very smart people to somehow narrow it down. So the idea is incredibly simple. It's like, well, let's look at something very similar to DFP, but work directly with H instead of B. So in some way, swap the roles of B and H, and swap the roles of Y and S. So in particular, if you think about the derivation that we just saw for, so let me keep this guy here. Actually, let me keep it like this. Let me keep the derivation for DFP here, okay? So here is the derivation for DFP. So you can think about doing the analogous for deriving H, where you would look for the H, that is the H plus, that is closest to the old H, okay, that is closest to the old H in some norm such that the secant equation is satisfied and the matrix is symmetric. So of course, this is like, find and replace, right? If I take exactly the same problem here and just replace all the B's by H and replace Y by S and vice versa, then the solution is going to be nearly identical. So let me put here, and for reference, let me put them both, the BFGS and the DFP. So let me put back the DFP. So the DFP update is right here. And the BFGS is here. So they're not identical. They're different. They're very closely related, but there is a subtle difference. The difference is that the form of the update for H in the DFP resembles the update for B in the BFGS. And the other way around, the update for B here is of the same format as the update for H in the BFGS update. Okay? Now, if you look at the equations for the updates, it is actually easy to see that the DFP, which is here, DFP preserves positive definiteness for B. That's kind of straightforward from this formula, that if B is positive definite, then B plus is positive definite. That follows from here, provided that the numerator here is positive. If you look at BFGS, it's also clear that if H is positive definite, then H plus is positive definite. It's the same argument. It turns out that the same thing happens with B, but then it's not as straightforward to see. So both of them preserve positive definiteness. So if we go back, if we think back to what I was mentioning earlier, right? What we wanted the Quasi-Newton updates to satisfy, we wanted them to be symmetric, close to the previous one, and positive definite. we check all of these with both the DFP and the BFGS. So both of them are good updates. In some way, the ones that they satisfy the properties that we would like to have. But BFGS turns out to have better properties than DFP. In particular, something that I'm not going to discuss because it just goes much more into the technicalities of the convergence properties is that BFGS has a certain kind of robustness properties. It has some kind of self-correcting property that, again, you have to get much more technical to really appreciate. So that's BFGS. So the broaden class is some kind of, SR1, DFP, BFGS. Those are some of many, many possible Quasi-Newton updates. The broaden class, broaden is the first B in the BFGS update. The broaden class is an entire class of updates that are of similar shape. So the broaden class, so here we have, again, BFGS. Here we have DFP, right? The broaden class is combinations of BFGS or DFP, which you can write in different ways. Essentially, both of them correspond to taking a parameter there to be 0 or 1. You can take a convex combination of BFGS and DFP. The SR1 actually corresponds to a particular value of phi that is not between 0 and 1. It turns out that many, many of the updates within the broaden class share certain properties. For example, properties concerning that they preserve positive definiteness, and a few other properties. So that's the broaden class, a whole class of Quasi-Newton updates. All right, so enough for now about all these different guys. Let's go back to the original problem because, this is very nice, right, to think about all these different updates. But this is not the main goal, right? The goal of the updates, let's go back to the beginning, right? The goal is to solve that optimization problem. And in some way, what we do to solve that optimization problem is maintain, in some way, expand our space of variables. We have the variables, the main variables x, and we are generating iterates for x. But we are expanding that to actually also approximate the Hessian, right, the B's. So this is a kind of a standard Quasi-Newton method. We choose an initial now x0 and b0. And then at each main iteration, we solve for the step, right? This would be a Quasi-Newton step. pk would be bk inverse gradient of f xk, negative sign. Then we pick a step length and update x, and then we update b. So that would be a standard kind of algorithm, Quasi-Newton algorithm. So what do I want to tell you about that algorithm? So of course, if you kept b to be the identity, right? If b was the identity at every step and we didn't bother to update, then this would be gradient descent, right? If b were the identity, that would be gradient descent. If b was exactly the Hessian, right, then this would be Newton's method. If b is updated with BFGS or DFP or any of the broaden class, that is a Quasi-Newton method. Okay, so that's why at the beginning of class I said this is sort of in between first and second order. It's like a 1 plus delta order method. Okay. So here is the main, one of the main theoretical properties of Quasi-Newton methods. So let me put this back here, the algorithm, right? So the algorithm is here. Again, if we looked at the special case when we don't update and we use the identity, that would be gradient descent. We know that that has linear convergence. If we used the full Hessian, that would be quadratic convergence under suitable assumptions. It turns out that if we make certain assumptions on the objective function, then we don't quite get quadratic convergence, but we get something that is far stronger than linear convergence. We get superlinear convergence. So it turns out that if we start with a sufficiently nice problem and we choose the step length appropriately, then we get superlinear convergence. Superlinear convergence, meaning that the ratio of each iterate to the previous one that goes to 0. If that stayed constant, if that ratio was bounded above by a constant, less than 1, that would be linear convergence. That's what happens in the gradient method. If the ratio of, say, the numerator to the square of the denominator stayed bounded by a constant, that would be quadratic convergence. That's what happens for Newton. Here we get something that is in between. So that's superlinear. And it turns out that this property of quasi-Newton methods relies on a more careful choice of step length. So, oh boy, I have another typo here, and this is really bad. So there is the type of, say, this is sometimes called the Armijo decrease condition, right? That you have seen before. When you choose the step length, we do backtracking until this condition is satisfied. But then there is also this other condition that ensures that the steps are not too small. These two together are called the Wolf conditions. And I should apologize. This is another typo here. There should be a T here. Okay. The Armijo condition should the Wolf conditions are the Armijo condition for this and this other condition. And again, this ensures that T is not too small. This one ensures that T is not too large, the first one. The second one ensures that T is not too small. And these are called the Wolf conditions. So the key technical theorem, I'm not going to prove this because it gets very, very technical, but it's just a sketch of how the superlinearity property holds. Essentially, something cool happens here. If we don't need to compute exactly, so the pk doesn't have to be exactly the Newton, the pk doesn't have to match the Newton step. It suffices if the difference between the gradient at f and the Hessian times p divided by p, it suffices if that goes to 0. If that goes to 0, then we can take steps of length 1. The steps of length 1 would satisfy our step length conditions. And eventually, after a certain threshold, we get superlinear convergence. And then the key technical fact is that both DFP and BFGS, they ensure that that condition holds. So both DFP and BFGS get us superlinear convergence. Of course, provided that we choose our step length carefully. So this is maybe the most important theoretical property of quasi-Newton methods, that we get something that is theoretically stronger than gradient descent. And in implementations, that is also evident. That again, we will give you maybe an example, an exercise with that in the next homework. You will see how the quasi-Newton updates can get you much faster to the solution than if you just used a first-order method, if you just used, say, gradient descent. Okay, so that is BFGS, DFP, and so on. So what I'm going to do next is I just have a few minutes, so I'll do what I promised was going to be maybe the last topic that I was going to talk about today, and that is limited memory BFGS. So next, I'm going to talk about a tweak on BFGS, and that's limited memory. Before I go there, if there is a question, this would be probably a good moment to ask questions or comments. Yes, back there.
At what point does it become more sensible to do the Newton method instead of Quasi-Newton? Is it just based on how cheap it is to compute the Hessian? Or maybe is it ever cheaper to do the Hessian than it is to do these DFP or BFGS updates?
So it typically has to do with, in so traditionally, one of the main places where Quasi-Newton gets used is if computing the Hessian is complicated. In certain particular problems, you have a function is complicated enough that evaluating the function is expensive. Evaluating the gradient is already quite expensive, but maybe you can afford that. But beyond that, it's just the process of evaluating would be an enormous calculation. For example, it could involve a whole simulation or something, something very involved. Or it could involve solving a partial differential equation. It could be very, very numerically, computationally expensive. So in those kinds of problems, that's where Quasi-Newton methods have traditionally been most effective. The very problem that prompted the development of Quasi-Newton methods was something of that sort. It was a certain problem in physics. So there are some physical applications that where that happens. The computation of the Hessian is the most critical part. There is another issue that has to do with what I'm going to say next, and is in certain cases, the dimensionality of the problem makes it be very, maybe infeasible or overly costly to have an entire n-by-n matrix and to deal with that system of equations. Maybe that is overwhelming. So in that case, you want something that is almost as cheap as just using gradient information that doesn't require equations. So those are, so both reasons really play a role in practice. All right, so let me talk about BFGS. So let's go back to to regular BFGS. So let's see if I can find it. So here is regular BFGS. Yeah, so here is regular BFGS. So limited memory BFGS turns out to be very popular, and it's especially getting a lot more attention lately. Things in several topics in optimization have this way of getting out and back in fashion. So BFGS, and in particular LBFGS, is one of those. So the idea is very simple, is that, so here is BFGS, okay? So think about either the update on the B itself or on H. And we are actually going to work with H because we don't want to explicitly solve equations. We want to use the inverse. Then we want to work with H. So the idea of limited memory BFGS is that we will maintain we will not maintain, keep updating the Hessian matrix or the inverse Hessian. But we will only use information of the last few iterates to update H. So even the updates could become too costly if we have a really huge problem, if we are to store the entire Hessian as a dense matrix. Even that could be too costly, just storing it, even if we are not going to solve equations with it. So an alternative is to have some kind of implicit, more compact representation of the matrix using only a few vectors. So to motivate that, let's go back to BFGS for a moment. And remember that in BFGS, this is the update, right? And at the end of the day, this is how we use it, right? We use H to compute P this way. So H, the Hessians that we are approximating, the Hessian inverses that we are approximating, we are using them to compute our step lengths, our directions. The P are the directions in which we move. We really care about the P. So if you think about how H is updated, here is a simple calculation. This is a very simple calculation, but it turns out to be actually very useful. Yeah, so let me keep, oh, it's here. So let me keep this guy here. Let me actually put it here. So think about what is involved in computing H plus times gradient. So when we want to compute H plus times gradient, it turns out that if you look at what H plus is here, right? Maybe I'll write down, yes, I have a few minutes, so maybe I'll write this down because this is kind of important. So a little observation here. If you look at H plus times G, right? H plus, I'm just going to write down what this is. This is I minus S y transpose S times H times this and y transpose S and plus S, all of that times G, right? Plus S transpose G divided by y transpose S. Okay, so let me write this down, maybe just one more step here. So let's see. You can write that down as I minus S y transpose S, right, times H. And then this guy here, you get G minus Y times S transpose G over Y transpose S. Okay, so that's what you get. So this product is equal to that term. Okay, and then here you get that term. So that's S transpose G divided by Y transpose S times S. Okay. So if you call this guy Q, if you call that guy Q, then it's easy to, and you call this guy alpha. So this is what we call alpha. Okay. Then it's easy to see that you can compute that product by first computing alpha equal to that. Then you compute Q equal to this. That's G minus alpha times Y. Then you compute P equal to HQ and this beta. And to finally compute H plus G, you take P and subtract alpha minus beta S. Okay, so so here, then you get that this is I minus S y transpose S times this whole product is what we call their P. Okay, and then we get alpha S. So if you think about for a moment, you get P plus alpha minus beta. So this is P plus alpha minus beta S, where beta is this guy here, Y transpose P divided by Y transpose S. So the key is that if you think about it, so if you already had H, essentially what you have to do to compute H plus is go this way, compute your alpha, compute your Q, then use H, and then compute beta, and then update P that way to compute your matrix vector product. So now if H itself was a BFGS on an H minus, then you just have to do an extra step, another layer of alpha, another P and Q, and another beta. So if you think about it for a moment, you proceed inductively, you realize that you can compute the product H plus G by two loops, each one of length K, if the H you obtained after K BFGS updates. So if you think about that for a moment, this is something that maybe takes a couple of minutes, or maybe if it's me, it will take you probably, if it's someone slow like me, it will take maybe 10 times more, like 20 minutes, to see that, okay, at the end of the day, these two loops get the job done of computing the Hessian, the H, Hessian inverse H times gradient product. Okay? They would get the job done exactly if we left the loops go up to, say, length K. So the LBFGS is this really cool idea, is why don't we limit the size of those loops to just M, where M typically is going to be, of course, smaller than K. So M in practice could be like 5 or 10. You just use the last. It's like if you limit your BFGS updates to use only information from the last 5 or 10 updates, 5, 10, or 20, something of that order. So this is the LBFGS algorithm. This matrix here is some kind of initial approximate inverse Hessian matrix. And the extra dependence here on K is because we can make it depend on K. A very popular choice, in fact, is to choose it to be a multiple of the identity, where the multiple is this guy here. And that is the LBFGS algorithm. Okay? LBFGS is, again, it's a tweak of BFGS where we are only using the information of the last few gradient iterates. All right. I had initially planned on telling you something about randomized, no, sorry, not randomized, but stochastic Quasi-Newton. But I'm going to skip that altogether. Ryan may say something about stochastic methods later, so maybe we can squeeze it there. We'll skip that. This was the main thing that I wanted to tell you about Quasi-Newton methods. So let's stop here, and we'll reconvene next week.